Hello, good morning, good evening, good afternoon, wherever it might be. It is my great pleasure to welcome speaker on site, DEVARSHI MUKHERJEE, who came here all the way from the city of good air, from the capital from Buenos Aires, the capital of Argentina. And today he will treat us to p-ADIC operator algebras. The Zoom is yours, the floor is yours, take it away.
Hi, thanks for the invitation. It's a pleasure to finally be here in person. Okay, so let me talk about some ongoing joint work with Alcides Bus and Luis Felipe Garcia. And yeah, so the idea is to do some kind of operator algebra theory. We don't yet know how much can be done, but I'll start with the absolute basics and show you the kind of theorems that could arise in this context. Okay. Okay, so the aim is exactly what I said.
Just that you know, the collaborators are with you.
Right, okay.
Oh, perfect.
They can chip in if asked anything. Okay, and what's special about such algebras over arbitrary Banach algebras? It's that these are some class of subalgebras of bounded operators on a Hilbert space. So by E. I mean, if somebody is wondering why I'm writing at 0.5x the speed I'm talking, it's because I'm writing on a digital blackboard. So just be patient.
Yeah, this is our trick to slow down a speaker.
Yes. Okay. Right. I mean, now the question is, what do I mean by a Hilbert space in this p-ADIC setting? That's one of the questions I'll try to answer. Also, I mean, to have any examples of operator algebra, I also want to define non-separable Hilbert spaces. So that's something to keep in mind.
So you mean this subcategory in a loose sense, somehow?
Well, yeah, some subcategory of
Kind of
Banach algebras which sit inside this, and define which category I mean. Yeah. Okay, so that's kind of the broad aim. And yeah, so let's get started. Okay, and yeah, maybe let me start with some motivation.
Hilbert spaces, usual Hilbert space or not?
In
For complex
I
numbers?
mean, it should be analogous to the.
Analogous, okay.
As of now, we don't know what a Hilbert space is. That's something I'll define in the p-ADIC setting. Okay, but before I get there, let me discuss some motivation. Okay, well, one motivation is to, of course, well, there is a lot of operator algebra theory over the complex numbers. That's not something I need to motivate too much in this seminar. And the kind of question I want to ask is how much is in some sense specific to the Archimedean case. And well, where does this kind of a question come from? Already in the case of, say, Banach spaces, we know that any Banach space, say over the p-ADIC numbers, is isometrically isomorphic to continuous functions vanish, well, yes. So let's say finitely supported functions on some set. This should not be F.
Yes, you cannot erase with your fingers.
This is QP. D subset. Okay, and of course, if you work over the complex numbers, such a statement is manifestly false because you have a whole hierarchy of LP spaces. So in this p-ADIC setting, what we know is that any Banach space is just one of these things. So there's no distinction between the LP unit ball for different P's. So in a sense, there are no interesting well, you can define these things, but they're all CZ.
I guess that your LP and your QP mean different P's.
Yes, so this is Q spaces.
Write down the condition of being QP vector Banach space. What is the condition for the norm? No, homogeneity for the norm.
Yeah.
Could you write it down?
You mean this condition?
Yeah. A times some vector. p-ADIC norm.
p-ADIC norm. Okay.
Any questions?
This will be p-ADIC norm.
Yeah, that's the norm, which makes that topological.
Yeah. And yeah, I mean, while I'm at it, this norm should satisfy the strict triangle inequality. That's what distinguishes QP things. So it's a stronger triangle inequality. Okay, so that's one thing that's special about the QP work. And I mean, this has kind of consequences in itself. So what this suggests is that the only type of completion you should care about is the C0 or the p-ADIC completion.
But what do you mean by C0? Because
yes, so
a set.
So this is only a it's just it's as a discrete space.
Finite support.
Yeah, finitely support.
Okay.
Then those will be like any functions, right?
Yeah, finite.
Finally support any function, but finally support.
Yeah, because compact in discrete topology means finite.
Yes.
Not finitely supported. Are all functions that go to zero, and going to zero at infinity means that for every epsilon there is a finite set such that everything
Outside the finite set is less than epsilon and norm.
Ah, okay, thank you, yes.
So is there a restriction then for the topology of D or
It's discrete.
Yeah,
is discrete? Oh, okay.
I mean, I can write it down. It's just.
So so the C in C0 should be lowercase.
Yes,
I think
By infinity, you mean what?
yeah, let me just write it down.
Some alpha filter?
Functions such that for any epsilon, there exists some finite set such that for all x in the complement of this. All such functions with the supremum length.
Yes.
Okay. Right, so basically the p-ADIC completion is the only natural kind of completion.
May I have a question?
Mhm.
Aren't functions of finite support dense in this
Yes.
topology? Okay.
So you take the p-ADIC completion of this. Okay, and right, so that's kind of one difference with regards to completions. And a related thing is, of course, with tensor products. That's another thing that arises. So over C, you have the maximal and the minimal tensor product. Minimal. And well, one is defined relative to the left regular representation or using an embedding of an algebra into bounded operators on a Hilbert space, and then you take the minimal C star norm. And the other one is, yeah, the maximal C star semi-norm on the algebraic tensor product, and then you complete with respect to that. Now,
I have a question. So this maximal and minimal refers to the operator algebraic setting, yes, not in the case of Banach spaces, since there is also
yeah. So this is for C
Banach.
star. Yeah, this is all operator algebraic.
Okay, thank you.
Otherwise, you have the completed projective tensor product for Banach algebras. And well, it's kind of natural to ask what happens over C, because in over QP or in the non-Archimedean setting, related to exactly this, that you don't have so many completions, and the completed projective tensor product is the p-ADIC completion of the algebraic tensor product, in some sense. So it's again an equally valid question: what are tensor products? And when I say what are tensor products, there's of course the usual one, which is the completed projective tensor product. But yeah, the question in a sense is, what are the other tensor products, if at all? If not, then it would be an interesting thing to know that everything is nuclear in the usual sense. Okay. So yeah, these are kind of questions one can import from usual operator algebra theory to this non-Archimedean setting. But there's more intrinsic motivation.
Sorry, so the first point was stated. The second point is a question.
Yes, that's a question.
Are you going to answer this question?
Yeah.
Yeah,
Okay.
no. Touch the screen again, screen. And touch the plus.
Which plus?
Well, no, this one.
Great.
Yeah, great. So you have only 19 blackboards left,
Yeah.
but that's just you will get only 6.
Yes. The speed I'm going, let me see how much of my own stuff I cover. Okay. Right. So as I was saying, there's also some intrinsic motivation one might have. And this is something related to what Andreas Holm and his student worked on some time ago. And in a sense, we picked up this project from where they left it. But let me pose what the problems are that they're trying to address. And these are lifting problems. Let me pose it first as a kind of meta problem. If you have let's take the category of algebras over a finite field. And let's say you have a problem that you want to address in this realm, you can lift it to p-torsion-free ZP algebras. And why might you want to do that? It's because you can do some analysis over here. So you can take different kinds of depletions. And yeah, then of course the hope is that you can come back to this world and say something about it. That's posed as a meta problem, but let me actually fill in something there. Of course, if you've done algebraic geometry in this context, then you know that there's a lot of work going on in this area. But in a non-commutative world, let's take the problem that Andreas and his student have been working on. Okay, so let's take the group ring where in their case they considered just a countable group, but let's say a countable discrete group. And you might want to know whether this has no non-trivial idempotence.
It's like Patterson Kaplansky, right?
Yes, yeah.
It's not that G is not just any group, right?
Yeah,
I have.
discrete group. Countable. Yeah, I mean, the setting, they considered it, they only talked about countable groups, but that's related to them having only defined separable Hilbert spaces. But I mean, the question makes sense for any group. And yeah, I mean, the conjecture is whether this has no non-trivial idempotence. Now, in the C star world, what you try to do is, you ask the same question and then you answer it using the reduced group C star algebra.
There's
Yeah.
a question from Jonathan.
That's
G
what I was saying. What Jonathan is saying, it's not just any group. If G
Yeah,
is finite and the order is not divisible by P, then it has lots of idempotence.
Yeah. Also, Alcides tells you to add torsion.
torsion free, right. Right. And of course, there's a lot of sophisticated machinery that goes on in proving the Patterson-Kaplansky conjecture in the complex realm. For instance, there's Mikhail Pushnik's work, which uses local cyclic homology in a very intricate way, which is then used to prove such a statement. And
sorry, do I remember correctly that it's also somehow related to bound-con?
yeah, I think one implies the other.
Bound-con implies.
Yeah. Okay, so
So I think that in particular, the surjectivity of the assembly map is related to this conjecture.
yes,
And injectivity is Novikov.
Okay. Thank you, Adam.
Right, and well, you can essentially ask, what does this type of an inclusion look like in the p-ADIC realm? And of course, the result that they proved is that idempotents lift to idempotents in a unique way. So that is unique up to conjugation. Okay, so I suppose that's enough for motivation. So there is this large class of open lifting problems that one can try to address using some kind of, well, a lift to a topological ZP algebra and then try to import C-star algebraic techniques. Okay, and well, there could be more things that come up, but these are the two things that strike my attention to by way of motivation. Okay, so let's now get started with what is the analog of X. Okay, I mean, I guess this depends on what properties of a Hilbert space you want to preserve. The properties I would like to single out self-duality. So that's one thing. And of course, an inner product is related in this case to self-duality. Right. So that's let's talk about. Okay, and what Andreas Thom and Anton Klausnitzer proposed was what such a thing should be, at least in the case where X is a countable set. But okay, we removed the countability hypothesis, which we needed for examples. But I mean, let me just point out Andreas's and Anton's work in this regard. Okay, so let X be any set. What we associate to such a set is the following abelian group. I guess non-empty set. And this consists of, of functions from X to QP. Such that f of X well, let's just say f of X belongs to QP. CP. Okay, so that's just some group, some abelian group, which is also a ZP module by the conditions that I've imposed. So this is a
Not an algebra.
well, I mean, we don't want our Hilbert space to be an algebra.
So this will.
Yeah, this will be the Hilbert space. So this is, but more importantly, it's not even a vector space. It's just a ZP module. It is a QP vector space when X is finite. But in general, this is just a ZP module. Okay, but this also comes with a canonical topology, which is, let's say, a restriction of the product topology.
In what sense did you say it was a group? With a sub?
Yeah.
Addition. VP model.
Yeah.
So point-wise convergence, right?
Yes. Okay, what is the topology? We call U inside UPX open. If for all finite sets, the following intersection.
Your P must be an F.
Yes, that is true. Okay. Right, so this is the topology. And if you know something about the Adels, then this is how you get a locally compact topology on the Adels. So that's where this kind of a thing comes from. Okay, so now this gathered is a topological ZP module. And yeah, as I said, this topology is kind of there to make the topology locally compact. So QPX with this topology, which I denote by tau,
Sorry, there's a stupid question. If X is finite,
then you just get the finite many copies of
QP, so it's a product, so it's a product topology or the topology of QP.
Yeah. So this is locally compact. Well, in particular, abelian group.
Is there an easy description of when a net converges?
Probably.
So it's not pointwise convergence.
No, it's not.
No.
No, it's inductive limit topology. So if net converges, it has to be supported on finite set. The convergence condition,
Yeah.
like for distributions.
I mean, there is a condition. It is like what was it, Richard, who said?
Yeah, it was.
It's like what Richard said, and we have it written down, but I don't remember it. But yeah, there is a convergence criterion. Okay, and where does this kind of guess come from that this should be the thing we should be after if we want self-duality? It's because there is a structure theorem on self-dual locally compact abelian groups. And this is the result was 69 that says that any self-dual locally compact abelian group I'll be loose about how I state this. Is one of these things or RNs or countable torsion-free discrete, some oops. Or direct sums and other combinations of these things.
Duality, what does it mean? I mean, is the dual?
It is an unspecified isomorphism with the dual
Yes.
existence of such.
Okay, so this is where this kind of a seemingly random looking thing comes from. This, if you're looking out for self-dual locally compact abelian groups, then this is where this shows up in that way. Okay. Right.
So from this point of view, these spaces are either like finite dimensional real spaces or spaces which are very big.
Yeah.
Because any D direct sum is dual.
Well, this is not any
What is
this is it's a countable like Z basically. Countable torsion-free discrete abelian group.
So this could be good, big.
I have a question. So it might be very trivial, but do finite groups with discrete topology fall in these categories? Like, do they fit the criteria because they are locally compact, alien?
They are countable infinite.
Yeah.
Okay.
They are excluded by definition.
Okay, we are restricted to the infinite case. Okay, thank you.
Okay, I mean, yeah, you can read this paper, it's like 5 pages and you can
Okay, no, it was just curiosity.
yeah. Right.
But wait a moment, you're right. So what about finite?
I think that the countable thing includes that, so it could be
So
finite. Yeah,
not necessarily.
yeah.
And
But the
most,
torsion that prevents it from being finite.
Okay. Yeah, okay, I'll have to check the precise statement, but if you want, you can add them to this list, but all this theorem is doing right now is justifying where this guy comes from.
In fact, it's a question of rough, but we are finite and billion groups. We are
Right. Yeah, so, I mean, yeah, let me just add this.
They must be here.
Yeah.
And even without this direct sum, it is dual.
Yes.
Yeah.
Yes.
Non-canonical, it is itself dual.
Finite. Yeah, okay.
So I guess the point is if you want it to be torsion free and not the reals and not an easily made up example, then you have to choose QPX. I suppose that's
Yes. Yeah. Okay. Okay, now let's discuss some properties of this QPX. Okay, yeah, I already said this in words. So this is finite, then QPX is a finite dimensional QP vector space. What's the product?
QP to the power x. All functions.
Cardinality. So what's the product of functions, right? Okay, and if the cardinality of x, and this was really the place where we picked up this project from. This is by Tom and Lausner. If this is the cardinality of n, then QP of x is a Polish group.
oh, okay.
Yes. I'm sorry, I guess I am allowed to ask this because I'm not there, but could you remind me what a Polish group is?
Yeah, it's a metrizable group, or let's say it's a metrizable group with a countable dense subset.
Oh, no, but completely metrizable in a
Yeah, it's
complete
complete as well. Yeah, complete. Complete metrizable group which has a countable dense subset.
So it's the same as a group that is also a Polish space with its.
Yes, yes.
Yeah, sure.
Yeah, so I guess like in light of this definition, this is the thing that leads to an analog of a separable Hilbert space.
Is there in this context some analogy between this complete orthonormal system of the Hilbert space and the fact that this axis of countable cardinality?
In but the ZP module that's not free. So when you say basis, what do you mean?
I'm asking.
Oh, yeah, no, I mean,
Because the reason
I mean,
why the
so far I haven't spoken about.
separable.
Yeah. I mean, so far I haven't even justified the full extent of why it deserves that name. So I haven't yet talked about an inner product. And only then would orthonormality. Oh, well, yeah, that's more intuitively what a Hilbert space is.
And then they will be a connection or another.
An orthonormal system.
Yes.
I don't know, but I've also not used it. So yeah, I don't know.
So if you're not using any sense of basis,
I think there is in their paper, there's definitely some mention of orthonormality. That's probably along the lines of what you're saying as well. Okay.
if you're not using any sense of inner product, you are defining the Hilbert space.
I am going to talk about an inner product.
Okay.
So far, these are just statements on the topology, but here comes the other topology, the non-topology. Okay, so
Yes, it's analogous. Okay.
Yeah.
yes. Okay, so we also have this p-ADIC norm on this, which is defined like this. And this makes sense because only finitely many things are allowed to be QP, the rest are less than 1. And with respect to this norm, QPX is complete. Okay. Finally, I do talk about this inner product. So there is a natural pairing. to S1, and I'll just get to that in a second. And this is defined as follows. Okay, well, a priori, this lands inside QP, because that's where the psi and the eta value. Then I mod out by ZP, so that only finitely many things remain. And then I finally use an embedding into S1, where the embedding is given as follows. So first I identify this thing with yeah, and then this is sitting in R naught Z to this one. So of course, this identification, there's some work to be done to show that, but yeah, the point is I then just take any one of these embeddings and I land in S1.
So, but it's theoretical embedding.
Yes. Yeah.
Forget about the
Yeah,
polish.
yeah. Okay, and this is symmetric. And well, I put this with the discrete topology, so it's also continuous. It's jointly continuous.
So this is rather like contracting
Yes.
duality, not like a scalar product.
Yeah, yeah. And the two are the same because I finally want a Lee's representation theory. So yeah, I'll just come to that.
So what is it, the symbol in front of a parenthesis?
One sec.
Iota.
Iota.
The embedding into the.
Ah, it's over there. Yeah, yeah.
Yeah, I don't. Okay. Right, so yeah, let me first state the.
Yeah, but maybe I was wrong suggesting that it's similar to contracting duality, because in contracting duality we are considering continuous characters.
Yes.
This embedding of QP mod CP into this circle is about two different topologies. One is p-ADIC and another one is
That's not contiguous.
yeah.
But
What about this?
Yes, Guillermo.
Please.
no. I don't understand I mean, it must be a very trivial thing, but the isomorphism between the completed thing and the uncompleted thing. Is it obvious?
Which
You
completely.
divide out the completion, the completed part. You divide out the P, right?
Mhm.
So you divide positive powers of P.
Yes.
So you have only finitely many negative powers of P left. That's why you get Z1 over P over Z.
Thank you, Richard.
So it is neither a scalar product nor contracting duality.
When you say not Pontryagin duality, what do you mean?
Because contracting dual is built with the continuous maps to the circle.
Yes.
But now you have this QP mod ZP embedded in something with Euclidean topology. This p-ADIC topology is.
This is discrete topology. This is not.
Discrete topology.
Yeah.
Okay. This changed.
Yeah. So it is this Pontryagin duality. So what we have
And sorry, a silly question, this iota, how exactly is defined? How do we embed it in the circle? I don't see it.
Well, through this isomorphism.
Yeah, through this isomorphism. No, this one.
Sorry, which one? I missed it.
This is iota.
Yeah, but how is
These
it?
are fractions with powers of p in the denominators,
Uh-huh,
modulo integers.
yes.
Mhm.
So I see them,
You can embed it in the circle.
Okay, and yeah, so now we have this Pontryagin duality isomorphism, which is Q, P, X.
says no, okay?
To modulo z, modulo z, to jest circle.
Hold on.
So
And the isomorphism is the one given by the inner product.
p squared, 2 over p squared, and that's filling the circle with such a function.
To say how it fills this circle.
So this is the Rees representation.
Yeah. Yes.
When I embedding this R mod z, which is the same as S1.
Okay. Yeah, makes sense. Thank you.
Okay. Good. Okay, now let's, so that's enough about this Hilbert space. So this Hilbert space is a topological ZP module with two different topologies. One, this restricted product topology, the other its own norm topology. And note that the norm topology is not this inner product, the square root of the inner product, because we don't have square roots in this world.
Sorry, so integral spaces have this isomorphism with the dual meant as a some dual space
Yes,
of functionals.
yes.
But now you have kind of functionals, but
Pontryagin, yeah,
only abelian groups, so no scalars, no
no, yeah,
bilinear in a sense.
no,
It's only Z bilinear.
yes, yeah.
And which topology does QP of X have there?
It was defined.
The usual.
It was no.
I remember. Yeah.
Product topology.
Yes. Okay. Yes. Perfect.
Okay, so now let's start talking about operators. Okay, so what do I mean by an operator? Let be linear. Continuous with respect to this restricted product topology. Okay, so that's what an operator is.
So this is a condition for X.
Condition B.
Condition six.
Six, sorry.
Yes,
So what is known about such sets X fulfilling this isomorphism?
I mean, nothing. Well, given a set X, you
Yeah.
can define this thing with its topology.
So this is this duality, this pairing is defined canonically.
Yes.
Okay. So the only variable in this is this X as a set.
Yes.
But is this an isomorphism for all sets or some of
Yeah,
them?
but for all sets.
So this isomorphism for all sets. It's a theorem.
Yeah, yeah, yeah.
Okay.
Yeah, okay, so, yes.
Yeah, that's all sets.
Okay. For all X.
Okay.
I guess I want non-empty,
It's nice.
but yeah, that I already said at the start. Okay, so, right, so we are at operators. And yeah, so the result is that, well, so what was the point of defining such an inner product? It was definitely not to use it to define a norm and then do the usual thing. But one thing one can do is talk about adjoints of operators. So the theorem is that any operator.
But when you say this continuous map on QP
Mhm.
X,
Yeah.
where does it land? The X again?
Yeah.
Would it be a big crime to say that this is an homomorphism?
No, no.
Okay.
No. There's an
Wait a minute.
endomorphism in the category of
These homes,
because there'll be more.
It's,
so these homes in the presentation,
Yeah,
they are automatically ZP linear.
yes, yes. So any operator defined in the sense as an adjoint. So that is.
using here this Reese.
Yes, yeah, yeah. And yeah, so I use the Rees representation theorem that gives me such an S by usual technique. But you have to work slightly harder when the set is uncountable to show that this S is continuous for this tau topology.
Ah, okay, okay.
But that's a bit
Yeah,
technical and
yes.
So I have a question.
yeah,
Context of a Hilbert space, if you have operator with which is everywhere defined, then the existence of the adjoint implies continuity. Is it also the
Yes.
case here?
Yeah, I mean, it turns out to be the case because I don't impose any further condition. But you need to do some work to show that it's continuous. It's not, well,
First, you have to define the operator norm.
right.
It's not so easy because it's not a scalar product. It's what?
Yeah. The scalar product does not give you anything continuity. Yeah, it just comes from an abstract existence result.
You don't have a norm of a vector even in this space.
On this, you do have a norm of a vector. It's this.
It was the, wait a minute. But this was a completely different norm. It was like
I can write it
a
as.
subnorm.
Yeah, that's the subnorm.
Yeah, so it's different from
It's not the tau topology.
nothing. So this is not related to the scalar product.
Not at all. Not at all. Yeah.
Is
Could
it how
one
you
use-
get used to
The characterization of
Completely new
the scalar
context.
product for the norm?
At least two people don't.
Oh, yeah, sorry.
I'm waiting. Go ahead.
Oh, yeah. Could one use then the scalar product characterization of the norm for operators in Hilbert spaces?
No.
maybe? No, not even that?
No.
Okay.
So there's no p-ADIC analog of this quadrilateral.
No, yeah, parallelogram, yeah, no, we have none of that.
Adam now. Adam,
One, the
Uh,
question.
I was only saying that it is hard to get used to this new context, only that.
Yes.
okay.
One little question. QPX with the tau topology
Mhm.
is colimit,
Is what?
or it's a colimit
Yes.
of, yeah, so product topologies, right?
Mhm,
So let's define it.
Yes.
Now, each of these things that is in the colimit is itself a completely p-adically complete, isn't it?
Yes.
So this is a bornological.
Yes.
Okay,
Yes.
and so it's a bornological space. So these are all the bounded in the bornological sense. Operators are all the CP linear bounded operators.
Yes. You'll have to specify the phonology.
Well, that's what I just said.
Yeah.
It's the collision of Banach spaces. So that's the
I mean, it has to be a phonological space because this QPX with.
I mean, you define the topology.
I mean, my impression was that.
No, but yeah, so it's not well, yeah. It's a colimit in as a topological space, but
Yes, exactly. So, I mean, there is however, a phonological interpretation of what boundedness is. So I mean, if you equip this with the phonology of pre-compact sets, then such a map preserves pre-compact sets. So this compactoid or pre-compact phonology, and then you get the same thing. So if I take the category of such maps, that is ZP linear and tau continuous, that's the same in some sense as bounded ZP linear maps, where bounded means preservation of pre-compact sets. But yeah, it won't be the norm phonology.
Sorry, what is a pre-compact?
I mean, the closure is compact. So in the tau topology.
I have a question. So do you have an analog of compact operators here?
Yes.
Pre-compact.
Yes.
Okay.
Yeah. Let me see how much time I have. Okay. Right.
27 minutes.
18 feet. Right. Okay.
What about the spectral theorem for such?
That I've never thought of. But you can think about it. I'll introduce the basic objects and then
The rest is
if you're good at that sort of stuff, you should definitely think about it. Okay, right. So now let me define a p-ADIC operator algebra. Okay. Okay, so p-ADIC operator algebra. Is a Banach ZP algebra. with an involution. That's the best way to do it. Such that there is an isometric well, into some let me explain what's going on here. So, okay, I guess I said this in words, but my B of QPX, given any non-empty set X, is the collection of D from QPX to QPX. Such that D be linear. And now continues.
And you think that for some chronology, it would be bounded.
Yes. For the pre-compact.
To come.
So B is more than equal than 1.
Yes, that I'm coming to. Okay, now this is just a ZP algebra. We can also talk about the operator norm on this. Operator norm is again, so recall that this also came with this supremum norm, so I can take things in its unit ball. And I can apply D to such things. This was my notation. Okay, and with this norm, this thing is a Banach ZP alpha.
But is T in this algebra if and only if the norm is finite or not?
I think no. I mean, this is always finite. I mean, this operator norm makes sense regardless. But no, this, yeah, I see your question. This data is not the same as operators from this viewed as a Banach module and taking bounded operators with respect to the norm monology. So no, that's slightly different. But I'll say something about how this is related to operators with norm conditions in a bit. So, okay, but with this norm.
So wait, so you say it's not the same, but is there an implication one way?
There is something I can say about them. It's not the usual thing where you take maps between Banach spaces and you just take the home inside the category of Banach spaces. But this is not that. Okay, and yeah, so to justify this notation, this is now just the collection of things with norm at most one.
And scalar multiplication by ZP does not change that since we're using
DP is
p-ADIC norm.
unit ball. So that has norm at most one.
Okay.
Okay. Right, now this has an identification with. If you don't want to know anything about this tau topology, then the following can be said. So this is just a collection of maps.
So this is just the unit ball, right? This be
Yeah, this is just the unit ball for this norm. So this is just a collection of, I think, Z linear maps or even just maps such that T is adjointable. And the operator norm is at most one. So in other words, this data suffices to talk about these ZP linear tau continuous maps.
Sorry, what do you mean by the adjointed? Not every operator you consider has an adjoint?
That was ZP linear maps.
Oh, okay.
Oh.
Yeah.
So that's why it's an isomorphism instead of an equality?
Yes.
Okay.
Okay. So yeah, I mean, this is not like a completely trivial isomorphism. It requires some work to prove this. There are some automatic continuity results. Yeah. But okay, this is why this is not automatic. You're only taking the Z linear maps here.
Yeah, but here you also take the linear maps, right?
In this one?
Yeah.
No.
No. So what are they?
So adjointable implies ZP linear or.
I mean, it will end up implying all these things. Yeah.
So that's somehow like in the classical Hilbert space.
Yeah.
Adjointable implies linear.
But you have to do it under this restriction of being the unit ball, right?
Yes.
Okay, otherwise.
Yeah, I mean, that's so that I get this. Yeah.
Yeah.
That's true. That's true. Yeah. You really need.
Your co-author says the isomorphism is an equality.
My what?
Alcides says the isomorphism is an equality.
Equality. Okay. Okay. I mean. Yeah, okay, yeah. I think the point is that this will turn out to be automatically tau continuous and let Z be linear. So yeah, in that sense, it's an equality. Yeah. Yeah, thanks. Okay, so that's this. Okay, now the definition is complete. So you just take algebras which isometrically embed into one of these things. Okay, let's take some examples. The base case is, of course, if X is finite.
Sorry, there was a question from Jonathan.
Yeah.
So with this definition, QP is not p-ADIC operator algebra.
That's true. Yeah, I mean, yeah, exactly.
Yeah.
Right, so if X is finite.
X is equality, so I see that.
That's
Yeah. That's that. Right, so if X is finite, then there's B at most one QPX can be identified with MNZB. So in particular, ZB should be the thing you should think of as the trivial operator algebras. Yeah.
So this is rather analogous not to Hilbert spaces or vector spaces. It's about lattices, in a sense.
Why?
Because of the ZP, there's p-ADIC integers.
Yeah. I mean, what do you mean by lattices?
Exactly.
If you have these subgroups, which after tensoring with R are all spaces, okay? Then you could think about these as lattices, which tensored over ZP with QP would be analog of probably of Hilbert spaces rather. Or not. It would be.
I mean, yeah, no. Short answer, no. Long answer, we can discuss over dinner. Okay. But no, that wouldn't work.
So you cannot introduce QP linear things here. Only
I mean, the moment you work with QP vector spaces, these kind of completion operations, they kill everything. So that's kind of a medium length answer.
Okay.
But I suppose you can, after you have your algebra, your operator algebra, you can tensor it with QP.
This we can do. Yeah, after you do everything that you want to do, then you can tensor it with QP. And that's what we do when we do, say, cyclic homology.
Okay.
So
I want very slow.
Yes. Right. So that's
at this stage.
Right. Okay. Not at this stage. Okay, the second example, which is the motivational example as well. So this is if G is any group. You can talk about the complex, the p-ADIC group ring. This is sitting inside B of QPG. And then you take the p-ADIC completion of this. So this is not the p-ADIC operator algebra, but rather C0 G Z. So this is a p-ADIC operator. And this is the analog of the reduced group C star algebra.
Is the inclusion, I mean, some multiply on the left or on the right by G before?
Yes.
Sorry, in this first example,
Mhm.
what would be the result if you would take the whole B, not just the unit ball?
MNQP.
I mean, QP, exactly. This is what I'm expecting.
I mean, yeah, I didn't say too much about why we are doing this unit ball business, but I mean, one reason is that when you talk about tensor products and you take, say, this minimal tensor product, then you want to still lie inside, let's say, B of QPX times Y or something like that. And to define the tensor product of two operators, you need them norm upmost one. So that's one reason why, to begin with, we just take things inside. It's unit ball of bounded operators on it's p-ADIC Hilbert space. Okay, and then yeah, maybe another example.
So, sorry, the example for a group would be the reduced operator algebra, right? It's analogous to the reduced one.
Yes.
Is the one too?
Is what?
Is there also an analog of the full?
Yeah, this is unclear as of now. So in this case, also the von Neumann algebra turns out to be the same as this reduced group C star algebra. But I don't know if there's any other thing that can be constructed. But yeah, basically you take the left regular representation, you extend it to the group ring, and then you take the p-ADIC completion. That's this map.
Yeah, so it's the reduced one.
Yeah, yeah. Okay, well, maybe last example, and because so far I haven't really given any example of an operator. So if I take the unilateral shift.
Yeah, I have a message from Alcides, I guess, but full group algebra turns out to be the same.
Okay, yeah. Thanks. Okay, yeah, I mean, this is just the usual unilateral shift. And the other shift is its adjoint. So that's the right shift.
Sorry, I have just a very silly question.
Mm-hmm.
When you write QPG, I mean, you define QPX for X being a set. So how do you use the group structure in QPG? I
mean, here's just a set. So
Yes.
inside QPG is just a set.
just a set.
Not this.
Right. So yeah. So the analog of the tuplets algebra is just the p-ADIC completion of E with T star. Okay, that's
So you mean if you take the closure of the algebra generated by T and T star inside B of QP of N,
yes.
then you get the same as you take the abstract algebra defined by generators and relations and p-ADIC
Exactly.
complete.
Exactly.
Oh.
So you mean ZT of this?
Yeah.
ZT algebra.
So you use the covered representation of that.
Okay, that's the last example. Now let me, okay, and you can generalize this to groupoid algebra. Get Levitt path algebras in the process also as an example of this. But yeah, I won't say anything more about examples, but we move on to one last thing I want to say in the next 5 minutes, and that is, well, the enveloping operator algebra.
Ah,
I mean, here some p-ADIC phenomenon shows up, which one does not have to deal with in the complex setting. So, I mean, why we arrived at this was because we wanted to ask whether this category of p-ADIC operator algebras is, well, does it have all limits and co-limits? So it kind of gets for free all the products and the co-products because it's sitting inside the category of contracting Banach spaces. And also kernels come for easy. It's easy to show that it has kernels. The problem is with co-kernels. So let's say you have, at a purely algebraic level, the following map.
So then this is the problem in topological groups.
Yeah. I mean, yeah. So the point is you create. Yeah. And this can never be a Banach algebra even because you can't define a non-trivial norm on something which has positive characteristic. Okay, so now what does one do to kind of remove these bad quotients? You need a construction which kills all of that. And that's given by, well, that's one thing that the enveloping operator algebra construction does. And of course, you also want to know that if you start with a star algebra, so what you want is, I'll write it in shorthand notation. So let's say this is the category of p-ADIC operator algebras. I want something here, a functor, such that if I take a p-ADIC operator algebra, I get the same thing as ordinary star algebras from A, B. Okay, so this is something I want, and how do we get such a thing? Okay, so let's say we have a star algebra with.
So it's about some completion.
Yes, with a star homomorphism from A to to one of these guys. Okay, and using any such star homomorphism, I can define a seminorm.
And the star is all the time defined by this adjoint, right?
Yes. And the star on ZP is the trivial involution.
Yes. Okay, the ZP conjugate.
Yeah. Okay, and this is just some semi-norm. Then I can complete A in the semi-norm first. Where, well, I mean, I can't complete interesting directly, but I first need to divide out the kernel. So given such a semi-norm, I can just take the set of X in K such that rho is 0. And now I define some A rho as A modulo this thing. And then I complete in the quotient.
You could use completion with respect to the semi-norm, and then dividing by the kernel would be automatic.
Yeah, basically. Yeah.
Will you eventually take the supremum over
Yes.
rho?
Yes.
And not every, I mean, I suppose that not every star algebra admits a faithful pi. So
yes. And this is not yet known. Yeah. Yeah. Yeah, but in principle, this could be the 0.
yeah, but even if you take the supremum, for some, even if you take the supremum, it
Yes.
may be that some pathological A's
Yes.
is still not a norm.
Yes, yes, that's true. Okay, so you complete in this and you get, well, just something that's complete in this one. Okay, and then you finally want to take what Willie said, which is the supremum. Yeah, I mean, now assume that you have a bunch of such star homomorphisms. Then you can define the maximal norm, which is analogous to the maximal C star norm. So this is the supremum by A, where,
Well, you already defined rho just above, so.
okay, then I should change notation. Where rho is some,
Size rho.
yeah, psi is some rho as well. I mean, we call these rows p-ADIC operator seminorms. So you just take all possible p-ADIC operator seminorms, take the supremum, and then what you get through this process is this universal gadget which satisfies this universal property. And yeah, this still acts on one of these QPXs. You essentially take the disjoint union of all the Hilbert spaces corresponding to these psi's. So this is a p-ADIC operator. Okay,
Is it true that the image of A in AU is dense?
image of, yeah,
But maybe this homomorphism is not injective.
yes. I mean, also, we found an example in which if A was a p-ADIC operator algebra to begin with, it is not necessarily true that A is AU. So you have to do the U again, and then you have AUU is. But anyway, the point is that now, if you take something over FP, that is, if you run into this situation, then this construction kills such things. And yeah, I mean, with that, this category of p-ADIC operator algebras has all limits and codes, just like the category of C-star. And well, so I guess I'll just say this in, no, maybe if you have two, what we can do with this p-ADIC operator maximal semi-norm construction is, well, we can define the maximal tensor product, which, as I said, was some motivation to consider such operator algebras. This would be this P. Well, you just take the algebraic tensor product and the enveloping integral. Okay. And well, yeah, I'll leave this as a question for now. How does this compare with?
And with tensor product in between A and B, in parentheses, it's just what up, right?
Yeah. With minimal or just the completed projective tensor product? Okay, so with that, and stop.
Thank you so much.
Thank you.
All right, any further questions? First from Harun. Tomek, I have you still on the.
I have a question.
And then you.
Yeah. So in page 8, this is a this is very simple, but I did not get that part. So in the second example, what did we gain by saying that G is a group now?
That was exactly my question. I don't know.
Okay.
I mean, you just have a, you can ask the same question also over the complex numbers. I mean, where you have a map from the complex group ring to
But
reduce.
You need the group structure to define.
And you got a representation. That's what you got.
You need the group structure to define the representation, right? It's a left regular representation.
Yeah, so you need the group structure. Yes, that's also another thing. You need the group structure to define the left regular representation.
Okay.
Okay.
I guess you can do it for semi-groups.
Yeah, and that's how we, well, I mean, the map is really defined from here to here, and that's the left regular representation. That's the thing we linearly extend and then continuously extend to C0.
Yeah, you just have to think about QP as L2. This is,
Yeah. Of course.
Yeah, so I mean, yeah, think of QPG as L2G.
and then, yeah, so the group structure is inside this representation.
Yes, yeah.
And in page 9, this is just, I know it might be probably a very difficult question, but for these, like for example, the algebra you said that was not equal to its universal enveloping algebra. So do you have some kind of idea for what kind of property will characterize the algebras that do equal their universal enveloping algebras, you know? Some characteristic of the universal enveloping algebras in general that could ensure like the closeness on this operation.
So I guess if a given algebra is already the universal involving algebra, some star algebra, then you apply this universal, that probably.
Okay, yeah, makes sense. But is there something like that is maybe easier to see? Like,
Yeah, I mean, not yet, not.
okay.
I think even more should be true, that if you have an operator algebra
Yeah,
and you regard it as a star algebra, and then you are taking a U, it
Yeah.
should be the same as.
no, this is the counter example we found.
There is a counter example. So
This is the counter.
So,
okay.
so the point is why call, so the definition of operator algebra should imply that AU is A. So if there are more examples, then these are second class examples. The good ones are the ones that are equal to its
Yeah.
AU.
Yeah, exactly. So the good ones, that is, say, the group algebra and its completion, that for that A is AU. Yeah, so any interesting example that we've tried, like the examples that I mentioned as examples of p-ADIC operator algebras, for that A is AU, but yeah, for some reason we found some finite dimensional example for which A is not AU. I don't know. So yeah, I guess then the question is, what are good p-ADIC operator algebras?
yeah. Thank you.
But please correct me if I'm wrong, but when you take this universal enveloping sister algebra in the usual realm, when you take the universal enveloping sister algebra of a sister algebra, it's just the same. Right?
Yeah.
Yes, every star more than back of board.
Right.
The counter example was. Okay.
Exactly. Star homomorphism is contractive. This is something we don't have in this.
Okay.
Yeah.
Okay.
So I have two questions.
Okay.
So first.
You two have two questions.
Yes. If you have this star algebra and you have this norm, so the natural question is a question of the C-star condition.
That is, yeah, that does not hold. If you were going to ask.
Not true.
Not true.
Not true. There is no C-star condition. Okay. Second question is about, if you think about commutative, such algebras, p-ADIC operator algebras, do you have something similar to
NS.
Gelfand-Naiman?
I mean, well, so far we don't have an abstract definition of what a p-ADIC operator algebra is. So at the moment, it is just some sub-algebra of bounded operators on a Hilbert space.
Yeah.
I guess your question is, if you started with some Banach algebra, then what further stuff do you need to put on such a Banach star algebra such that there exists a GNS representation?
No, GNS is okay. I could live without GNS.
Okay.
But I couldn't live with Gelfand-Naiman.
Yeah, I mean, I guess the version of Gelfand-Naiman would be the one from analytic geometry. That's at least one of them. So if you have a rigid analytic space, then these correspond to certain Tate algebras. So which are portions of p-ADIC completions of polynomial algebras of the
So affinoid spaces.
Affinoid.
The analogs of compact spaces.
Affinoid spaces would be spaces, yeah.
I can live with it.
Yeah.
It's really a justified.
But yeah, that has nothing to do with p-ADIC operator algebra. I mean, I can take the spectrum, which would be the Berkovich spectrum, and take continuous functions on that. And then, yeah, I can find a representation. Yeah.
Wait, there is a question on Zoom. The example we have for AU not equal A is indeed commutative.
Right. Yeah. Yeah, I mean, the example is you just take this matrix. 1, 1, 1. one in the two ADIC integers. And take the algebra generated by this and the identity. In this, it turns out that the enveloping algebra gives you something else.
Anybody else in here?
Yes.
Go ahead.
So if I understand correctly, so basically you said, no, your analog of the Hilbert space is this QP of X.
Yes.
And you showed that on this you have some kind of inner product.
Yes.
Is there also a possibility to go the other way around? So to say, if we have some abelian group with some pairing into S1, is there a possibility to complete this to a Hilbert space, something like this? I think this would be something unique for some GNS.
Yeah, this would be needed for a GNS construction, you're right, and I don't yet know how to do it. Yeah, but this would be an interesting question.
And something else, I think maybe I misunderstood this, but I think in the beginning you mentioned once or twice that you were looking at, well, you're interested in a non-Archimedean setting.
Yes.
There I'm wondering, what do you mean by this? So non-Archimedean ordered.
What I mean is that my norm is a non-Archimedean.
Yeah.
Just because of the, okay.
Yeah.
I was missing where there is.
Right.
Anyways.
p-ADIC, p-ADIC is non-Archimedean.
Yeah, but it's only.
Yeah, so all
Was it-
these norms, for instance over here, I only take.
Exactly. I checked it on Wikipedia when.
Okay.
Makes
One general question. These properties, these nice properties that sister algebras have, that they automatically have approximate unit, that any star homomorphism coming out of them is automatically continuous.
Yeah.
Hold for your p-ADIC operator algebras?
I mean, the existence of approximate units, that's not something I've ever thought about. The automatic continuity should not hold because I think it holds in the C-star algebra case because of the C-star identity. On the other hand, if it holds, I wouldn't know why it holds. So yeah, I would imagine that this is not true. At least not for these morphisms. So here my morphisms are also just morphisms of the underlying algebra, the underlying Banach star algebra.
And are any of these p-ADICally complete algebras that we all know about examples of operator algebras in your sense? Say I take CP, or I take, I don't know, ZP of G and I p-ADICally complete it.
Yeah.
This is not one of those, right?
This is one of those, yeah.
Like this.
Yes, it
But
is.
it's not a reduced sister algebra, or is it? Or the group. Because the completion.
Did you say groupoid?
No. I take the group algebra and I p-ADICally.
Yeah, I mean, this is the C0GZP example, right?
Yeah. But is this the same as the reduced sister algebra?
I think so, yeah.
Ah,
Yeah.
oh, okay.
Yeah, I mean, like the recipe to come up with examples of these p-ADIC operator algebras is just take some star algebra given by generators and relations, and then just p-ADICally complete them inside well. Yeah, I mean, that's how the Stokelitz algebra example came about.
So Ewing can sometimes be the same as p-ADICally completed. By Ewing, I mean,
Yes,
I
yes,
want to-
yes. Yeah, exactly. So Ewing and p-ADICally completing, I want to know next when these are the same. But for instance, in the group algebra case, this does turn out to be the same.
So what exactly turns out to be the same?
The p-ADIC completion and the U or something.
Ah, the universal. Okay. I had a problem understanding EU. This was you can. Not looking now. Okay.
Yeah, well, that's exactly a natural question that it's doing.
Adam,
I mean, but by the way, if Ewing is the same as p-ADICally completing, then for let's say some nice algebras, then for those algebras, this completed projective tensor product should also be the same as the maximal tensor product. So it's also related to this thing that I raised as a question to everybody.
Adam,
Yes, what about the spectrum of an element in such operator algebra?
Beginning this question.
Well, the spectrum of an element is non-empty.
Is what?
Uh,
Sorry?
What's that?
The spectrum is, I didn't have.
non-empty.
Non-empty.
Non-empty, okay.
Yeah. I think it's also compact. So these are all ancient results of Berkovich.
Mhm.
Yeah, but there's a lot that's known about the spectral theory of elements.
Sorry, but what is this spectrum? Because
Yeah,
algebraic,
Yeah.
at least the algebraic completion of p-ADIC numbers.
No, yeah, it's the Berkovich spectrum,
Mhm.
which is
Okay.
defined as set theoretically, that's a collection of semi-norms on
Mhm.
some algebra. And
Oh, but this is not something similar to the spectrum in the context of ordinary case over C.
no, this, yeah, it's Berkovich spectrum.
Okay, so
You
this is
can talk about the Berkovich spectrum of any Banach ring. In particular, if you take a commutative complex, so C0x, and you take its Berkovich spectrum, then it recovers the Gelfand spectrum. But yeah, the more general notion is the Berkovich spectrum.
Oh, but if you are saying Gelfand spectrum, you mean the spectrum of the whole algebra, yes?
Yes.
But I mean just simply the spectrum of an element. You take an element in your operator algebra, and then what? In the complex case, you have a spectrum of an element.
So this should be the spectrum of an algebra, right?
Yeah, I mean, you'll have to compute some determinant equation, which may not be solvable because your field is not algebraically closed.
Mhm. So it
So
might
you'll
be
have to work
empty.
in some finite extension, add roots. Yeah. Yeah, this does not quite behave the same way. So the notion that carries forward is this Berkovich spectrum.
Mhm. Mhm.
And yeah, when I said it's non-empty, I meant that
Yeah,
spectrum is non-empty.
Okay, so but what about the spectrum of the self-adjoint elements?
Oh, for example, yeah.
Shouldn't this be the spectrum of the algebra it generates?
Yeah, it should. Yeah, I mean, of a single element, I imagine this is what it should be, but yeah, I wouldn't claim to know this concretely.
So at the beginning, I asked the question
Yeah.
of the spectral theorem for a self-adjoint element.
Yeah, no, I don't really know of a
So
precise
sorry, Thomas,
spectrum.
I somehow miss it.
Oh.
Sorry.
Yeah, but yeah, if that question interests you, you should start thinking about it.
I have also one more question about the notion. So you have explained something which is more like a C-star algebraic construction. How about von Neumann and
Yeah, that is
topology?
also, yeah, we're working on that right now. So yeah, and I'll give a follow-up talk sometime about what I know for Neumann algebra. Yeah, I mean, I don't know how much time we have.
Okay, so this is work in progress, yes?
This is work in progress.
Okay, okay, thank you.
May I have one more question? If you think about different positions of rational numbers, then you can have these p-ADIC norms and this Euclidean norm at infinity, the place at infinity.
Yes.
Okay, so could you put this construction or all this construction for all prime numbers
Yeah, so Adele,
together with this theory of real Hilbert spaces into one family, like in Archimedean?
yeah, so you mean is there a Adelic version of what I'm now calling QPX, whether it can be A of X?
Yeah, so
Very-
there's some,
very Adelic.
is there some global notion?
I mean, the global notion is A of X, where A is the Adels. This is your R and P is prime.
Yeah, but
So, I mean, you'll have to then talk about A of X and write a separate paper on this. But I mean, at the moment, we're still here. But yeah, this is, of course, a natural question, whether there is some Adelic theory.
because probably know this, there's a subject in mathematics which is called the arithmetic geometry.
Yes.
And then you have something, some construction which sews together all
Yeah, sure.
p-ADICs and this. So at the infinity, you have this Hermitian geometry, which is close to the theory of Hilbert spaces. Okay, and then you have some geometries over finite fields, for instance. So
Yeah, I mean, well, if your question was, is there such a theory? I would say not yet.
not yet.
Yeah.
Okay,
I mean, there isn't even a theory of QP yet.
but it's a natural perspective for.
Yeah, that is this talk. So this is
Okay.
QP.
Mhm.
Yeah, what happens when you take everything together? Interesting question.
Okay, anybody else? Guillermo, Richard?
I'm
Actually,
fine.
Yeah, actually, Guillermo's question, is QP an p-ADIC operator algebra?
No, ZP.
No, okay, good. Yeah, okay.
Willie?
Okay,
You are happy?
I'm happy and going eager to enjoy the bright afternoon.
Good for you.
Okay, so if there are no
Okay.
other questions, let us thank our speaker again.
Bye-bye.
Bye.
Let me stop the recording.